Welcome to discussion 20. In today's discussion, we'll focus on section 4.2 on the mean value theorem, or MVT. And in this video specifically, we'll do a practice problem where we show an equation has exactly one root. So let's begin by recalling the mean value theorem. This says that if we let f be a function such that, and there's two conditions. The first is f is continuous on the closed interval from a to b. And the second is f needs to be differentiable on the open interval from a to b. So no sharp corners, no cusps, no vertical tangent lines, that sort of thing. Then the conclusion is then there is a number. There is a number c in the open interval from a to b such that the derivative of f at c will be equal to f of b minus f of a over b minus a. So let's draw a picture to illustrate what this is saying. So if I go to a picture, I'm going to draw some axes. Okay, so I'll have an x-axis and a y-axis. So let's say that this is a, this is b, and I have some graph. Maybe that looks like this. And here's the point at b, and my graph looks like this. Okay, so in the context of this graph, this point where x is a is going to be a comma f of a. F of a will be the y-coordinate. And at b, that point is b comma f of b. So if we look at the conclusion of the mean value theorem, the right-hand side, this f of b minus f of a over b minus a, that's the slope of a line. It's the slope of the line that connects this point with this point, and that is a secant line. So this is a secant line. So the right-hand side represents the slope of the secant line, and the left-hand side is a derivative that represents the slope of a tangent line. So this equation is saying that there's some point c between a and b where the slope of the tangent line is going to be the same as the slope of the secant line. In other words, they're going to be parallel. So if I look at the graph, sort of just looking at it, that seems to be somewhere here. If I draw the tangent line, it looks like that's going to be parallel to the secant line. All right, so this is my C. So more precisely, this mean value theorem says there will be at least one point where the tangent line is parallel to the secant line. So in my picture that I drew here, there's just one point, but there could be more than one depending on the shape of the graph. All right, so let's do a practice problem. All right, so here is our example I want to look at. And in it, I want to show the equation 5 minus x to the 7th power plus 5 minus x equals 5 has exactly one root. So there's exactly one value of x I can plug into this equation that's going to satisfy it. All right, so I want to talk about the idea for this before I give you a chance to pause it and try it. Okay, so if I want to show an equation has exactly one root, the classic strategy is to show the equation has at least one root first. And we can show it has at least one root using IVT, the intermediate value theorem, and we've done problems like that before. And then we will show the equation has at most one root. At most one root, and that we'll do using MVT, the mean value theorem, and a proof by contradiction. And a proof by contradiction. So that said, let's get into actually showing this. So we are ready to begin the proof. Okay, so for the proof, let's start with the first part. Let's show that this thing has at least one root. And this is where I'm going to ask you to pause it and try the problem on your own. So pause the video just for 3 minutes to try this question on your own, just showing that it has at least one root. 4, 3, 2, 1, Pause it for 3 minutes. See if you can show this as at least one root. It's going to involve intermediate value theorem. Alrighty, so hopefully you did that. Let's talk about it together. So I'm going to start off by calling this whole thing on the left-hand side, where all my variables are. I'm going to let that be my function, f of x. So I'll let f of x be 5 minus x to the 7th power plus 5 minus x. Okay, and I need to show that this function equals 5 somewhere. And to do that, I need to find a couple of inputs. I need to find some things that I can plug in for x, such that I need one of those outputs to be bigger than 5 and one of those outputs to be smaller than 5. Because if that happens, then somewhere there's going to be an output that's somewhere I'm going to reach 5 as an output, as long as my function is continuous, and this function will be continuous. Alrighty, so I want to plug in some simple values of x, and I'm actually going to plug in 5 first, rather than 0, because it's really easy to simplify what I get if I plug in 5. Plugging that in, we'll get 0 to the 7th, and then 5 minus 5 is 0. 0 to the 7th plus 0 is 0. Okay, and that is less than 5. So now I need to plug in something that would give me an output that would be greater than 5. Okay, so if I plug in something like 6, I'll get a negative number being raised to the 7th. And that's going to make this whole thing negative, and this 5 minus x, that'll also be negative if I plug in something like 6. Okay, so I might try plugging in something smaller, like 4. It turns out if I want something bigger than 5, I'm going to need to go to a number like 3. If I plug that in, we get 2 to the 7th plus 2, and 2 to the 7th plus 2, that is way bigger than 5. All right, so now I can say that my function here, this function right here, this is a polynomial. And a polynomial is going to be continuous everywhere. My function f is continuous everywhere. So it's going to be continuous on the interval I want to apply IVT to. It's going to be continuous on the interval from 3 to 5. All right, so I say something like by IVT, by the intermediate value theorem, there is a number c that is in the open interval from 3 to 5, so it's between 3 and 5, such that when I plug that number c into my function, I want to get the output, this output 5. All right, so we have now just shown that our function has at least one root. We are done with the first part of showing that it has exactly one root. So we're ready for part 2. We are ready to now try to show it has at most one root. All right, we're ready for part 2, showing that it has at most one root. So I'm going to give you a chance to pause it and try this. Pause this one for 7 minutes to try it. 4, 3, 2, 1, pause it and try this for 7 minutes. All right, so hopefully you did that. Let's talk about it together now. So I mentioned earlier that we're going to tackle this with a proof by contradiction. So that the way that begins is we suppose, for the sake of contradiction, that the opposite of what we want is true. So the opposite of what we want is, let's suppose that our equation, our function being equal to 5, has, if I'm trying to show that it has at most one root, the opposite of that would be at least 2. So let's suppose that this has at least 2 roots. At least 2 roots. So let's call them something. So let's call them A and B. It might have more than 2, but at the very least, we're assuming that it has 2. And I'm going to call those 2 A and B. Okay, so these numbers need to be different, which means A is not equal to B for them to actually be 2 roots. Okay, and because these are roots, that means, because they're roots of this equation, that means f of A is equal to 5 and f of B is equal to 5. So next, we're going to try to apply the mean value theorem. To do that, I need to first check the conditions for MVT. Okay, and our function here was this polynomial, and a polynomial f. This is going to be differentiable and continuous everywhere. So we can apply the mean value theorem to any interval. We can apply MVT to any interval, and in this problem we're going to do it to the interval from a to b. All right, so the interval from a to b. All right, so by MVT, the conclusion is there is a number C that's an element of the open interval from a to b, such that f prime of c is equal to f of b minus f of a over f of a over b minus a. All right, so this gives me f prime of c equals, and f of b and f of a were both 5. So we have 5 minus 5 on the top, and on the bottom we have b minus a. So 0 divided by the denominator is non-zero because a and b are different. That's just going to be 0. So the mean value theorem tells us, well, there's a point where the derivative is equal to 0. And typically the way that these arguments go when we do a proof by contradiction is, now we want to show this leads to a contradiction. Okay, so it would be nice if I could somehow show that the derivative never actually equals 0. That would definitely be a contradiction. All right, so let's remind ourselves what our function was. F of x was 5 minus x to the 7th power plus 5 minus x. Now let's take the derivative. So the derivative of this, I'll need chain rule for this first term. 7's going to come down. And I'll get 7 times 5 minus x to the 6th. Then I multiply by the derivative of the inside, which is negative 1. And then the derivative of this 5 is 0, and the derivative of the minus x is minus 1. So that's my derivative. And this, I could just simplify. This is negative 7 times 5 minus x to the 6th power, and then minus 1. All right, so I want to be able to show that this derivative is never going to be equal to 0. So I can actually just logic that out. There are a few different ways I could approach it, but one is I can use some logic. Because I have this whole thing being raised to an even power, that means that is definitely going to be greater than or equal to 0. And because that's greater than or equal to 0, this implies that when you multiply it by a negative number like a negative 7, negative 7 times 5 minus x to the 6th, that will be less than or equal to 0. Okay, so now when I subtract 1 from it, so this implies that negative 7 times 5 minus x to the 6th, when I subtract 1 from it, all right, so subtracting 1 from it, if I subtract 1 from both sides, we'll get that this is less than or equal to negative 1. So what we've just shown is that our derivative, whoops, sorry, there should have been a negative here, negative in front of that 7. Our derivative, this was our derivative, is always going to be less than or equal to negative 1. So there's no way it can be equal to 0, like what was supposed to happen because of the mean value theorem. So this contradicts. This contradicts the fact that f prime of c is supposed to be equal to 0. And once we reach a contradiction, that means the assumption that we started off with was wrong. So it follows that our assumption that the equation f of x equals 5 has at least 2 roots is false. And because that's false, so that means that f of x equals 5 has at most 1 root. And that's what we needed to show to be able to complete the argument. Because earlier we showed this as at least 1 root. Now we've shown that it has at most 1 root. And if both of those are happening, that means it has exactly 1. So therefore, remember these 3 dots are our symbol for therefore. Therefore, the equation f of x equals 5 has exactly 1 root. And that is what we wanted to show. So I'll write my little square shaded in to indicate I am done with the proof.